Hi everyone. Today's video is about an application of the theory of determinants as we have developed it so far, which is Cramer's rule. At the end of the video, there's also a little something about block matrices, which are a possible shortcut for some of the situations that you may find yourselves in. Let's get to Cramer's rule. This is a procedure to compute the solution of a linear system, AX equals B, using determinants in a very smart way. So here's our notation. Let's say that the solution is the vector U with entries U1 through UN. To compute those entries, we can do the following. We define certain matrices MI in the following way. For every MI, we erase the ith column of the matrix A that we start with, and we replace its entries with the entries of the vector B coming from the linear system. In other words, MI is obtained by replacing the column AI in the matrix with B, the vector B. And then what Cramer rule says is that to compute the ith entry of the solution, of the solution vector, U, all that we need to do is to compute the determinants of the matrix MI and of the matrix A, and then divide one by the other. Let's have a look at an application of this formula to the following linear system. Well, from the linear system, we start by setting up what the matrices are that are involved. This is 0, 2, 5. To compute the entries of the solution, we will need to find and compute the determinants of matrices M1, M2, and M3. Maybe I'll just write them down, and then we can compute determinants. M1 is what I get by substituting the vector B, 1, 2, 7, into the first column of A. M2 is obtained similarly by substituting 1, 2, 7 in the second column of A. And the third vector M3 will have the same two columns as A, but the third will be replaced by the vector of constants, 1, 2, 7. Okay, for each one of these, we want to compute the corresponding determinant. For example, for my matrix A, I want to do a cofactor expansion along the first column. So I get 1 times the determinant of 0, 1, 2, 5, minus 2 times the determinant of 1, 1, 2, 5. This number is minus 2. Minus 2 times 5 minus 2, that's 3. So it's negative 8. Let's compute the determinant of M1. And maybe this time I can do a cofactor expansion along the second column because there's a 0 there. So I will get minus the determinant of 2, 7, 1, 5, minus 2 times the determinant of 1, 2, 1, 1. Computing these, I get 10 minus 7, that's 3, so it's a negative 3. And then I have 1 minus 2 is minus 1 plus 2. So that's a negative 1. Let's compute the determinant of M2. Again, I'll do a cofactor expansion, this time along the first column. So it's going to be the determinant of 2, 1, 7, 5 minus 2, the determinant of 1175. When I wrap these up, I get 3 minus 2 times 5 minus 7, it's negative 2. Last but not least, the determinant of M3. I'll use a cofactor expansion towards the first column. So we get the determinant of 0, 2, 2, 7 minus twice the determinant of 1, 1, 2, 7. And this becomes negative 4 minus 2 times 7 minus 2 is 5, which is minus 14. Okay, we've computed all of our determinants. We can now write out the entries for our linear system. So x1 will be the determinant of m1 divided by the determinant of a. The determinant of m1 is negative 1. The determinant of a is negative 8. So I get minus 1 over minus 8, which is 1 over 8. X2 is the determinant of m2 over the determinant of a. The determinant of m2 is 7. So this becomes minus 7/8. And x3 has the determinant of m3 over the determinant of a, which is minus 14 over negative 8. So it becomes a plus. Okay, that was an example of an application of Cramer's rule, but let's have a look at why this rule should work. And here's the reasoning. The setup is ax equals b with solution u1 through un. To convince you that this will work, I define this new matrix ui, which is obtained by the identity with the ith column replaced by the vector u. So I will just stick the vector u in there. Now, let's take a moment to think about what the determinant of ui is. To compute this determinant, I can do a cofactor expansion along the column u, but you start to see immediately what happens. So if I look at cofactors through this column, for example, let's have a look at the first one. I must erase the first row in this column to compute it. So what's left, maybe I'll draw it in green, is this matrix here, which, if you pay attention to what the entries are doing, has the first column, which are just zeros. And then in the second, there's a 1, and then there's a bunch of zeros up until the end. Yeah. So we get something that looks like the identity, but with one column of zeros. That seems right. Yes, we need to be a little bit careful with the sizes, but what's for sure is that the first column of this matrix will be 0. And if a matrix has a column of zeros, then its determinant is 0. So, and this will happen for every one of the cofactors, except for the one at the entry ui. Because when we are at the entry ui, the cofactor CII will be the determinant of an identity matrix, n-1, because I will be erasing exactly the row with ui in it and the column with all the u's in it. What's left is an identity matrix. All of the others will have a column of zeros. take some time to think about this and maybe write down a simple example of a 3x3 matrix. The determinant of this matrix UI is in fact going to be just the entry UI, because when I take all of my cofactors, the only one that survives is UI times CII, and then I have all of the others, UJ times CIJ, but all of these are 0. And CII is the determinant of an identity matrix, so this will be a plus 1. The determinant of UI is little ui, so let's use that fact and set up the following thing. Let's take A times the matrix UI. The matrix UI has columns the standard vectors except for the vector U. So when I multiply it, I get A times E1, A times E2, A times U, and then all the others are just A times En. But these are nothing but the columns of A. A times E1 is A1, A times E2 is A2, A times En is An. All of them are the columns of A except for A times U, which is B, because U is a solution of the linear system. But this is exactly the matrix Mi, because Mi is obtained by A, from A by replacing the ith column with B. Therefore, A times Ui is Mi, so the determinant of Mi is the same as the determinant of A times Ui, which is the determinant of A times the determinant of Ui, which we just said is exactly little ui. In other words, by solving from Ui, we get that it is the determinant of Mi over the determinant of A. And that explains Cramer's rule. I just want to comment very briefly about a possible shortcut that may appear sometimes, and in those times it may make your life a little bit easier. Sometimes matrices have some sort of block structure. In this matrix here that I wrote down, you can see that there's 3 by 3 blocks in it that allow us to write it very simply. We write A as a matrix of matrices of 3 by 3 blocks, where, well, two of the blocks are the identity or a scalar multiple of the identity. One is a block of zeros, and the other is a matrix B, 4, 7, 9, 5, 8, 1. The left-right block. Block matrices sometimes make computations easier. If I were to square this matrix A, I can write it down as a block matrix, and I can multiply the matrices in the block using matrix product. So for this entry here, I would have that's I times I plus 5I times 0. So that's I times I, which is I squared. For the second entry here, I would have I times 5I plus 5I times B. So I would get 5 identity squared plus 5B, because the identity times B is just B. And down here, I would just get 0 times 5I plus B times B. It's a B squared. So we would reduce the computation of computing the square of A to computing the square of B, which is a 3 by 3 instead of a 6 by 2. It's a similar procedure with the determinant. In fact, we have that the determinant of A is the same as the determinant of this block matrices here, which is the same as the determinant of the two blocks multiplied by one another. So this would be the determinant of I3 times the determinant of B minus the determinant of 0 times the determinant of 5 times the identity. But this part clearly vanishes, and the determinant of I is 1, so this is the determinant of B. More in general, whenever you have a matrix which is a block structure like this with two square blocks, and it's important that they're square, B and D, then you can compute its determinant as the product of the determinants of the two blocks. The reason why that's true is that whenever a matrix has this structure, BC0D, it can be decomposed into matrices that look like this: identity 00D, BC 0 identity. And then the determinants of these, since there's an identity, will just be the determinants of the little block. Maybe let's check that this decomposition is accurate. When I multiply these two block matrices with one another, I get identity times B plus 0, that's B. Identity times C plus 0, that's C. 0 plus 0, and then 0 times C plus D times identity. And that's, in fact, A, as we checked. A word of caution, not always identifying blocks does help you, but it may be helpful when you see a structure like this with 2 squares on the diagonal and then zeros of those squares. This is the end of the video. I'll see you next time.